what we're going to do now is we're going to try and have another go at a few Haber cycles. So what I want you to do in this section is to concentrate on you are trying to apply some skills. So the first skill we're going to try to apply is we're going to go back over the definitions from video 2, and I'd like you to apply those definitions and write your own equations for each of the changes listed in this table. Now in an exam you would just get this name of the change with the value at the right hand side. You wouldn't have a space to write an equation, but it's really good for you to get these Haber cycles right by knowing what each change represents. So please pause the video now and try to write balanced chemical equations with state symbols for each of these changes. So I've had a go and I've thought carefully about the definitions, so let's just go through each one. The formation of sodium bromide. So the definition says when 1 mole of the compound is formed from its elements in their standard states. So sodium bromide is formed from sodium and bromine, they're the elements. Bromine is a diatomic element, so it's Br2. Their standard states are solid, and bromine is one of the 2 liquids on the periodic table, so be careful, watch out for that one, L. And to balance that, without changing the number of moles of sodium bromide, because the definition said 1 NaBr, we have to put a half in front of Br2. The second change said atomization of sodium, which is when 1 mole of gaseous atoms is formed from the solid. So I formed 1 mole of Na gas from 1 mole of Na solid from the element. And the atomization of bromine, when 1 mole of gaseous atoms is formed from the element. So Br gas from a half a Br2 liquid. First ionization energy, when 1 mole of electrons is removed from 1 mole of gaseous atoms. So I've removed 1 mole of electrons from Na gas to make Na plus gas. Electron affinity, when 1 mole of gaseous 1 minus ions is formed from 1 mole of gaseous atoms. So 1 mole of Br gas plus electrons makes 1 mole of Br minus gas. And then lattice enthalpy of, and in this case we're being asked to do formation, so we're making NaBr solid from the gaseous ions. This is lattice enthalpy. The top one was just formation, this is lattice enthalpy, and lattice is from gaseous ions. And this is our unknown, so I'm going to give this a symbol X rather than a question mark. Mathematically that's my unknown. So what we've got to do now is put all of this onto the cycle. So for this example I'm going to work through it with you to remind you of the steps of putting it onto a cycle. So we're going to scroll right down. You'll be able to still see the table. I will not, but we will make do. So here we go, we've got our cycles drawn out for us. You will never have to draw this from nothing in an exam. There will always be some structure there for you, and some of the lines may well be filled in and you'll be filling the gaps. So my little rule of thumb is if I put my crystal lattice, my solid crystal lattice on the bottom line, so in this example it's sodium bromide, and I always say to myself I've got to work from the elements to the gaseous ions. So what elements are in sodium bromide? It's made of sodium and bromine. And what ions are in sodium bromide? Sodium ions and bromide ions. Now, they are gaseous ions, so they're separate. Over here, these elements are in their standard state, so sodium solid and bromine is a liquid, and now I need to balance it. So to balance this equation from the elements to the solid, I would need a half a Br2. What I'm going to do now is I'm going to go up to my table and look at the data I've got and see if I can find this particular enthalpy change, so this arrow that's pointing down here in my table of data. So can I find an equation where Na solid and a half a Br2 liquid turn into Na Br solid? And if I look at my table, that's the very top line of the table, and that very top line has a value of minus 360, and that makes sense because that arrow is pointing down, so it's a minus number. And I'm going to look in that table and see if I can find somewhere where Na plus gas and Br minus gas turn into, the arrow points towards NaBr solid. And that's the very bottom line that we've labelled X. That's the thing we're going to try to calculate. Okay, so now we need to work our way around the cycle And what we're going to do is we're going to go from the elements to the gaseous ions. We're going to atomise and then atomise again, and then ionise and then electron affinity. So atomise, atomise, ionise, electron affinity. So let's start by atomising our metal. So changing Na solid to Na gas without changing the bromine. And then we're going to look in our table of data and see what value is there for Na solid turning to Na gas. And the value that's in our table for that change is plus 109 kilojoules per mole. So I've atomised the metal. I'm going to atomise the non-metal. So Na gas I'm leaving alone, and I'm changing a half a Br2 liquid into Br gas. When 1 mole of gaseous atoms is formed from the element, that is the value that's written down here, that is 112. So atomise, atomise, ionise. I'm going to ionise the metal. If I do that, I'm going to turn it into positive ions. Don't forget the electron. And then I'm going to leave the bromine alone. And I go to my table and I see where Na gas turned into Na plus plus an electron, and that had a value of plus 494. So we're still going up with our positive numbers. And then the last change, if we look at this, the Na plus gas has stayed the same, but the electron and the Br have become Br minus, and that has a value of minus 325, which looks good because it's pointing down. And now we have our cycle. And what we know about our cycle is that the direct route, which is from the elements to the compound at the bottom, so this direct route here is going to be equal to our indirect route, which goes all the way up and round and down here. So we can write down our numbers. We don't need to write down all the symbols, we can just write down the numbers. So our direct route was minus 360. We followed that arrow down. That is also our anti-clockwise arrow. And then we're going round that cycle, 109 plus 112 plus, follow that arrow up, 494. We're still following the arrows, so the arrow, although the arrow's coming down, we're following it, so we're plussing what's written on the arrow. So we're plussing minus 325 plus whatever that arrow is. Now, looking at the direction of that arrow, our answer to x should come out to be large and negative because it's a big arrow pointing down, but at the moment we're just following the arrow. We don't know what the unknown is, so we say plus x. So we're going to do a little bit of adding up. So the thing we're going to add up, we can leave that for now, and let's just add up all the numbers on this side. So if you add up all of those numbers on your calculator, we should get 390. We've still got plus x. So you can now rearrange for x by taking away 390 from each side, and you should get minus 750 kilojoules per mole, which makes sense. It's a nice big arrow and it's pointing down, minus 750. So we're going to move on to a second example. This example is slightly different because magnesium chloride has 2 chlorines in it. Now that is going to make a difference in our cycle, but for now I want you to pause the video and write down the enthalpy changes that are written here as equations. So convert these enthalpy changes into equations. So pause the video now and have a go. So this is what you should have got. Now notice that in these equations, some of them have got 1 Cl and some of them have got 2 Cls, and that is where our issues are going to lie when we come to putting them on the cycle. So the formation has got a Cl2 in it, it's 2 Cls in total, but the atomisation of chlorine only has 1 Cl in it and a half a Cl2. Things aren't quite matching up, but these numbers and words are for the 1 mole version, And so it's really important that you get these equations correct. What we're going to do now is work out why and how we're going to take account of those 2's. So I'm just going to put that value of x in for our unknown, and we're going to start going and then start to see where things are going to be a little bit different. We'll just have a go. So again, we're going to scroll down, get onto our Haber cycle. I'm going to put my solid lattice at the bottom, magnesium chloride. I'm going to put my elements in their standard state, so magnesium solid and chlorine gas. And that is the numbers that you would need to make magnesium chloride. Put those on, and over on the other side I'm going to put my ions, magnesium 2+ ions and 2 Cl- gas ions. They're my ions. So from the elements to the ions, I always put those bits on first, and then let's have a think about what else we can put on here now. So straight away I can put the x on, that's our unknown, and immediately I can put on a value for this, turning the elements into the compound, and the value in our table for that is -641. Right. So remembering our little order, we're going to atomise and then atomise again. So atomise the metal, then the non-metal, then ionise the metal, and then do electron affinity to the non-metal. So atomise, atomise, ionise, electron affinity. We're going to atomise magnesium. It's going to become magnesium gas. I'm leaving the chlorine alone. So that process, Mg solid to Mg gas, is written in our table. Mg solid to Mg gas is written down, and the value in the table is +148. So we've atomised the metal. Now we're going to atomise the non-metal. And when we atomise Cl2 gas, leaving alone our magnesium, we're going to atomise, we'll end up with 2 Cl gases. We're turning it into atoms, separate atoms. Now, that equation is not written in our table anywhere. Half a Cl2 to 1 Cl is written in our table, and half a Cl2 to 1 Cl was +121, but we've got 2 lots of that, so we're going to put 2 times that value. Because we've got 2 moles, not 1 mole, and the value is for 1 mole. So I've atomised both things. Now I'm going to ionise. And because magnesium is in group 2, I've got to do 2 lots of ionisation energy. It's not 2 lots of the first ionisation energy. I'm not trying to make a 1+ ion. I'm trying to get to the 2+ ion. So I'm going to ionise it once by removing 1 electron. Don't forget the electron, leaving the chlorine alone. And then I'm going to ionise it again, and when I ionise it the second time, it becomes 2+. It loses another electron, so now there's 2 electrons floating around, still gas, and we still haven't done anything to the chlorine. Okay, so we can put the numbers on from the table for those 2 changes. And the first ionisation of magnesium is +738. And the second, where we remove the second electron, is +1451. What are the mistakes that we might see? We might often see not having 2 electrons on the top line because we think, well, in the equation we only have 1 more electron, but we've now got 2 in total. We had 1 and we've now got 2. So just be careful with that. Right, now we need to look at this last change here. 2 Cl gases are becoming 2 Cl- gases by picking up these 2 electrons. And in our table, we've got a value where 1 Cl picks up 1 electron, and it's -364. We've done that 2 times, so it's not a second electron affinity, it's 2 lots of first electron affinity, and we've got a 2 in there. So let's just have a look at the table and see how that links. Okay, so we noticed that we had a 2 in the formula after chlorine. If we go and have a look at the things that are to do with a single chlorine, and we look at those numbers, they are the 2 that we had to double. The ones that are to do with chlorine. Nothing to do with magnesium chloride, because that's 1 of magnesium chloride, which already has the 2 chlorines in it. We don't need to double that, but the ones where it's 1 mole of chlorine and we've got 2, we need to double. So mathematically now we need to do a little bit of maths, which is to say that the direct route, or the anti-clockwise arrow, the minus 641, equals all the other arrows added up together. So plus 148 plus, and don't forget that 2 lots of 121, plus 738 plus 1451 plus 2 lots of minus 364 plus our unknown, which is going to be a nice big negative number. So get your calculator out and have a little go. Minus 641 still here. Add up all the numbers on the left hand side, see what you get. I got 1851 plus x, so x equals minus 641 minus 1851, which is minus 2492 kilojoules per mole. So I'm going to end this video here. If you feel confident, you could try the next two ones in your notes. If you feel like you're going to need the support, there will be a further video that goes through the remaining two cycles in the notes and explains the little differences that you might come across.